All right, let's get started. How are you guys doing? A couple thumbs up. A couple woohoos. 2 thumbs up. Okay. Who'd like to offer a prayer for us? Thank you. Sure, just stand.
Father in heaven, we're grateful for this opportunity to learn some mathematics today. We're grateful for Brother Corey and that he helps us to relate it to things that we know and make it fun for us. We're grateful, Father, we have the opportunity to get an education at this university. We're grateful for the circumstances, Father, that allow us to be here, especially the Father to allow us to meet in person. We just ask you, Father, to send our spirits to attend this meeting so we can learn as much as we can and to help us pay attention and involve ourselves so we can get the most out of this presentation that Brother Corey has for us today. We're grateful for the privileges we have, Father, and we just ask you to help us to make the most of them. And we leave these things, Father, in the name of Jesus Christ. Amen.
Amen. Thank you very much. Quickly, any comments about the forum yesterday? Yes. You felt depressed. Yep, it was a very depressing forum.
It was like, oh, the US used to be really good at education, and now it kind of sucks.
Yeah.
So like, well, that was
I actually have a really, really nice slide that captures that. I didn't bring it. I actually thought about bringing it, but it shows like in the 60s, in industrialized countries, the OECD countries, if you know anything about those, but they're basically kind of like the 30-ish most civilized countries, most not civilized, most, yeah, whatever countries, the biggest kind of economic powers. And it shows how many people, what percentage of the population get a high school degree or equivalent in the different countries. And in the 60s and 50s, the US was by far number one. The US was the first major country to make a commitment to give everyone an opportunity to get a high school level degree. Korea was near the bottom, and they had like 27 maybe % of the people getting high school degrees. And every decade, the US, everyone else gets closer to America, then passes them, and US drops. So where we were number one, and that makes a huge difference in the economy when you have so many people with at least high school level skills. That investment paid off. But now we're like ranked right in the middle of the pack in terms of high school degrees. We were still pretty high in bachelor's degrees, but the same phenomenon is happening where a higher percentage of people in those other countries are getting bachelor's degrees, and we are slowly increasing, but they're passing us. So it's really depressing. Right? Korea is now number one, whereas 40, 50 years ago, or maybe 60 years ago, they were like near the bottom of those countries, and now they're number one in terms of getting people out with high school education degrees. So yeah, it was pretty depressing. Any other comments?
I don't know if this shocked anybody else, but she told us that we're the first generation since 1776 to be less educated than our parents.
Yeah. Pretty sad. So, yeah, in America, right? She's talking about specifically in America, and I don't take it like personally. If you're here at BYU, you're probably not, right? This is kind of as a whole thing, right? So, yeah, pretty depressing. Yes.
I find it funny how they like to group everybody in a big old group and be like, you're all uneducated, and then you talk to the university students who are pretty well educated.
Yeah.
I just find that like.
Yeah, so that comment, for those online, he said, I find it kind of interesting that you like to group everyone in the one big group, like we're all not as educated, but she's talking to kind of the highest echelon of educated students in the generation. So one way to make sense of America, there's a guy named James Q. Wilson. He's a very famous sociologist. He's actually one of the few non-members that have ever given a commencement address at BYU. And he has a very famous essay called Two Nations. And he argued that that America, do you know this? Oh. He argued that you shouldn't think, you should, the right way to think about America is that there are two completely different nations in America. Kids that grow up in a solid household that usually have a married father and mother, where they live in a safe neighborhood, they have opportunities for a good education. They don't have to worry about some of the, they're not in a crime-ridden neighborhood, et cetera. Their parents tend to be well-educated with a job where they don't have to worry about losing it in general. And then that's nation one. And then you have nation two. And nation two is you have kids, usually in single-parent homes, living in where the income is very low, high risk of losing what income you have. They're in neighborhoods where there's high risk of all of the bad things like crime, involvement in gangs, drugs, all of that stuff. And those are two totally different nations, and the problems in those two worlds are very different. And he said we lose a lot when we try to group those together. So, yeah, interesting. Yeah, it's pretty depressing. Hopefully you guys can do things to help out with those. Okay, let's start off with these problems. Hopefully we don't want to spend too much time on these. They're not going to change the world at this moment, but let's see what we can do. Yes, take 5 or 6 minutes and work on these problems of the day.
Have the tests been graded?
No. If you have questions, just raise your hand. I'm happy to help. It's about any of the material, not just these questions up here, but anything you read about. If you want to talk about, let me know. Okay. Let's go through this, and then we're going to talk about bases, and then I have some examples of where we can try to understand the row space, the null space, and the column space. What do they mean when we multiply, and why are they useful? So I started by row reducing. Okay, a lot of you started on this. Good job. Once I did my first step, that's actually enough for me, in this case, to know what the row space, to find a basis for the row space and a basis for the column space. Null space, we're not done yet. But row space and column space we can, and rank. So I did this. Here's our two pivot positions. I don't have to go all the way to reduced row echelon form yet. So here I have two pivot positions. So I know the rank is going to be 2. In a system, I would have a free variable here if I was thinking about AX equals B. So I would have a free variable. But for the row space, the basis for the row space, it's the set. So I heard someone say, how do you write a basis? A basis is a set of vectors. So we use the set notation, these curly brackets, okay, to talk about a basis. The basis for the row space, this is the easier one. We can take any of the row space, any of the rows that have a pivot position. And we can do it in any of these positions. Because each of these later ones are just linear combinations of these earlier ones. And so they're still in the row space. We can take them to be, put them as a basis. So I can do 1, 2, and -3. Or I can do a -1, 2, and 5. I'm sorry, not or. So that's one of them. Or I could take 1, 2, and a -3. 0, 4, and 2. Or 1, 0, -4, 0, 1, and a half. Any of these sets will work as a basis for the row space. Okay? The span of each of these as a pair will be a plane in R3, and that plane will be exactly the same plane no matter which of these pairs I take. Okay? So any questions on how to find the basis for the row space? Okay, how about the column space? The basis for the column space. So you have to row reduce until you find out where all the pivot positions are. But then you have to go back to the original matrix. Because row reduction, although it doesn't change the row space, row reduction does change the column space. So I have to go back to the original. So a basis for the column space will be 1 and a -1. Oops. And 2, 2. Okay, so that's a basis for the column space. Yes? That's right. Okay, so he was asking for clarification. He said because row reduction changes the column space, you have to go back to the original matrix. Yes. So what you pick out in the original matrix are the columns that have the pivot columns. So if there were 3 pivot columns, you'd go back to those 3 columns. If there were 7 pivot columns, you'd pull out all 7 of those. But you have to pull them out into 7 in these because it's not the same. The span of 1, 0 and 2, 4 is not going to be the same as the span of 1 and -1 and 2, 2. But for the row space, row reduction doesn't change the row space because you're just dealing with linear combinations of the originals. So there's no way to kind of get out of the span of these first ones. these are still vectors in this span. These are still vectors in this span, and they're still, you'll have the same rank for each of these, so it's not going to change the span. So, yes, Danny.
Does row reduction always change the column spaces? In this case, the column spaces are two.
Oh, no, so row reduction may not change the column space. Doesn't always change the column space, but you're not confident that it's the same. So, yeah, there might be cases where it doesn't, like in this, maybe the span is the same. But in general, yeah, I claimed it wasn't, but I was wrong. Thanks for catching me on that. So the span is R2 in both of these, but there are cases where row reduction will change the column space. So, yes. So that question was, if you know the rank of the row space, oh, you said row space, right? So how you can, if you span like a whole like all of R2 or all of R3, but like in this case, you have with the row space, you have some slice of R3, and it doesn't have like what you were calling an elementary basis. There's not, this isn't, you can't just take 1, 0, 0 and 0, 1, 0, right? That'll span the XY plane, but there's some Z element in here, so that won't work. So you could, here in this case, the column space is all of R2, so you could write down 1, 0, 0, 1. So, yeah. Does that help? Nice thinking. You ask good questions. Okay, other questions? Yes. So that question is, what if you wrote the column space as 1, negative 1, or the basis for the column space, and then 1, 1? That would be okay, because you're just taking a scalar multiple of this, right? The span will be the same. So yeah, you're okay. Bases are not unique. So there's infinitely many bases, unless it's just the point subspace. But yeah, bases are not unique. Scalar multiples of the basis vectors, they can still be basis vectors. Even linear combinations of basis vectors you can replace one basis vector with a linear combination of basis vectors. So they're not unique. Okay, other questions? Okay. Null space. Let's finish null space. So the null space, we can go back. The null space says what values of x, y, and z in this case get me the zero vector out. So I can go back and augment it with the zero matrix. I'm sorry, the zero vector. This is as far as I can go. It's nice because 0, 0 here, no matter what row reduction I do, what row operations I do, these will always stay 0, 0. And now I can rewrite this as x minus 4z equals 0, y plus 1/2 z equals 0, and z equals, I'm going to pick a parameter t. So this is what we were doing before when we had free variables, right? We have a free variable here. So I'm putting everything in terms of this free variable. I'll put x in terms of z and y in terms of z. So that means x equals 4z, y equals a minus 1/2 z, z equals t. So I'm going to replace those with t and write this in vector form. So replace those with t, pull it out. I get 4, a minus 1/2, and 1. So all of the points all of the vectors x, y, z that I can multiply by this matrix A are on this line, 4 minus 2 and 1. Right, if I take 4 minus 2 and 1 and dot product with this, I get 4, 4, a minus 1, a minus 3, and a minus 1 and a minus 3 is a negative 4. 4 plus 4 is 0. If I take this, dot it with this one, I get a negative 4, minus 1, so that's a negative 5. Dotted with the 5, I get 0. So that this null space here, all of the vectors, all of those points on this line. Okay, and this vector is the basis for the null space of A. Okay. If I had two free variables, I'd have two basis vectors. Right? If I had something where I had to do plus S 1 0 3, I don't know what it would be, right? Then both of these would be basis vectors. And then the null space would be a plane, the plane spanned by those two. Yes? Nope. Nope. The parameter captures captures the linear combinations, but the basis vectors are just these. No, basis vectors are not unique because I could scale this. I could multiply these all by 2 and get rid of that fraction if I wanted to. 8, 2, 1. I could pick that as my basis vector instead of 4, negative 1/2. And right, and it would do, yeah. We can scale these how we want. We can actually take linear combinations if we want, but generally we just pull those. But yeah, you're free to take scalar multiples of these. Okay. So null space. So hopefully this is a quick review of finding the basis for the row space, column space, null space. The rank was 2, we already talked about that. There's one more question here. Question 2, if you multiply vector x by A, we get out of vector B. So one way to think about matrix multiplication is it's kind of functional thinking. You have an input and you have an output. You've been doing this thinking for a long time, like y equals 2x. You think about x as the input and y as the output. That's very similar to ax equals b, and where b is our output and x is our input. We could do b equals ax if we wanted to, where this is the output, this is the input. But the idea is that x here is the inputs. We can think about the b vector as our outputs. Where does x live? If I multiply x by a minus 1, no, it's not a minus 1, positive 1, 2 minus 3, a minus 1, 2, 5. If I multiply x, if this is my x vector here, this is my b vector here, then where does this x vector live? What dimension does it live in? How many values does it need in there? So go ahead and hold up your fingers. So 1 for R1, 2 for R2, 3 for R3. Okay, lots of 3 fingers. That's good. How about my output? What do I get out? Where does this live? Yeah, R2. Okay. So yeah, I need an X, Y, and Z here, and I get like a B1 and a B2 here. So this could be, there's an example that the book uses about going to different produce places or different shops to buy oranges, apples, and pears or something. So this would be the number of apples, the number of oranges, the number of pears. This is the price of each of those, okay? Some guy's paying you $3 a pear to get rid of his pears, but, and then these would be the 2 shops that you're shopping at, and so here you'd have the price for each of those quantities at one shop and the price for each of those quantities in another shop. Your input is 3-dimensional, Your output is two-dimensional. Okay. The inputs and the outputs give us a way to think about, to better understand what the row space and the null space are. But we're going to take a break and look at bases first, and then we'll come back and talk about row space and null space. So the basis of a subspace, a basis is a minimal set of vectors that will span the subspace. It is like the Goldilocks situation where you have enough information, you have enough vectors that you can span the whole space. But you don't have so much that you have redundant information. Okay, so it spans the whole space, but it's the smallest set you can have that spans. Okay, so it's really, really nice. So we will use bases a lot for things, because if I have exactly enough information to span the set, if I have this minimal spanning set, then there's only one way. There's exactly one way to get to any point in that subspace. And it's really nice to have exactly one way, because then I don't have to worry about infinitely many ways. Coordinates, which we'll be reading about, coordinates are unique. So so once you have a basis, there's a unique vector, a unique coordinate for any point in the subspace. And you can think about bases as building blocks for a subspace. Let's look at a couple specific examples. So we've talked about visible spectrum before. Intuitively, I think this is a really nice place to talk about a basis. We can build the visible spectrum. To build it, we need 3 pieces of information. How we talk about those 3 pieces can be different. We can talk about how much red, for any color, you can tell me how much red, how much green, and how much blue I need. And I know exactly what that color is. And so red, green, and blue, I can think about those as my basis vectors for interpreting or making sense of the visible spectrum of colors. There's another basis, though. There's actually 2 other natural vectors: hue, saturation, and luminescence. The mathematics of those are actually nicer than the red, green, blue. You can also do the primary colors of blue, red, and yellow, which really are cyan, magenta, and yellow. So you have to pick the right blue and the right red. The cyan and the magenta and yellow are these stripes. Like you can see the yellow stripe. Then kind of in between the green and the dark blue, there's this light blue, that's cyan. And then in between the the blue and the red over on the right side, there's this kind of pinkish, that's magenta. So you can tell me how much of each of those I need, and I can make those. Each of those I can think of as a basis for visible spectrum. Okay. Why not red, green, blue, and pink? Because pink gives me information that I don't need. I can still get everything with red, green, and blue, and if I throw in the pink there and give you 4 coordinates, then there's infinitely many ways for me to write any value instead of just one, to write any color instead of just one. So not as nice. Let's pick a basis. Let's use a basis so that there can be exactly one way of writing the colors. A basis is not unique. We already talked about how there's a few different ways. This is not a subspace, unfortunately. The color spectrum isn't a subspace. They're not all linear combinations. They have maximum values, so it's not closed under scalar multiplication, for example. So the math is not linear, but the idea of this as a basis and taking linear combinations fits pretty well here. So linear combinations works, it's just not a subspace. So, and translating red, green, and blue to hue, saturation, and luminescence, that's not a linear transformation. We will be focusing on linear transformation between bases, but it's not a linear transformation, unfortunately. Otherwise, this would be really nice context to do these things in. So, just a little preview to coordinates this next time. What 3 numbers represent navy blue? Well, that depends on what basis we are using. If you give me 3 numbers, I have to know, well, you're talking about red, green, blue, or you're talking about cyan, magenta, and yellow, or you're talking about hue, saturation, and luminescence. they're like the units that we use. If you say how tall, you ask me how tall I am, and I say 18, you're going to be like, 18 what? Like, doesn't help me very much. Same thing with coordinates. If I give you a coordinate of a point, you have to make sure you know what basis I'm talking about. Now, standard basis are really nice. Turns out they're not always the nicest basis to use. So, there are other ones that are natural to use. All right, digital image compression. So JPEG compression, it uses a different basis for making up a picture. I thought this was so cool. So if you zoom in, you can see each pixel here on a black and white. You can see each pixel basically has a grayscale from basically from white to black. Okay, and you can think about this image as if for every single pixel you tell me how much gray there is. You know, the one value that'll, you know, like you can think of 0 as white and 1 is black or something, or where is it in there? You can do that. It turns out that takes a lot of information. There are ways to relay the same information, the exact information, without all of that. And the way you do that, that's more like what a bitmap does. Bitmaps aren't small files. What they do is they look at an 8x8 chunk of the picture, and they make up that chunk with these things. These are the basis vectors for building up an 8x8 chunk. And any 8x8 pixel value you give me in grayscale, I can make with some combination of those. If I have to take all of them, then I don't save much information because I have 64 of these. But it turns out, especially with pictures, natural pictures, the ones down here in the lower right rarely get used. And it also turns out, if you don't care about a little loss of information, you can cut those out. Even if you're using them, you can cut those out, and it doesn't change the picture that much. So then you can relay almost all the information with a lot less memory. So it also turns out each of these is orthogonal. So each of these contains unique information compared to the other ones. We'll come back to this when we talk about orthogonality. Isn't that just so cool? Who thought of that? I don't know. Sound waves. So that top wave is me saying hello or hi. And that's a vector. There's like, I don't know, maybe 8,000. I think it's 8,000K. Oh, I don't know, but maybe it's 4,800 hertz. Yeah, so maybe this every second, there's 48,000 pieces of information. And so for 1 second, I can write down each of the amplitude. All sound is how much amplitude there is at any point in time. So you can write down the height of those waves. And for every second, I'd have 48,000 of those. Okay, but I can compress those. I can make those sine waves. I can make that crazy hello sine wave with combinations of other sine waves. And this is when some of you will go on to learn Fourier analysis. It turns out you can build almost any function with sine waves and cosine waves, and they're really, really nice, especially periodic functions. And so it might take me 300 waves to get that hello or something really close that you couldn't tell the difference of. But if I can do it with 300 sine waves, then you just have to tell me the 300 pieces of information, and I can regenerate. You just have to tell me how much of each of those different sine waves I need, and then I can regenerate it, and that just costs you 300 pieces of information rather than 48,000 pieces of information to send me the exact data. That's a lot of what MPEG does. We actually have the tools to do this. I hope someday to do this in class. So the way you decide how much of each wave you use is actually a projection onto a subspace. So projections have to do with closest values. Okay, let's go to, oh, I have this already. Oops. Bold in the middle. There we go. Oops. Okay. I'm going to use this example to talk about the null space, the row space, and the column space of the first example we did. So this system here, 1 to a -3, -1, 2, and 5. Okay, I have it up there in the spreadsheet at the top. It says matrix. I've row reduced it. And so that is the same thing we got when we row reduced. These vectors down here, those are two vectors are the original row vectors. Okay, so 1, 2, and a -3, a -1, 2, and 5. So I think it goes this way. So red is x. So that point A should be 1, 2, and a -3. So 1 in the x, 2 in the y, and then it drops down 3 in the z. Okay, and B likewise. The row space is a linear combination of all those. So, so that plane right there is the row space. Okay. If I row reduce, I get two different vectors. These are my row reduced vectors. They're the 1, 0, and -4, 0, 1, and a half. And it's nice because they point in the x and the y direction, because they have a 1, 0 and a 0, 1 component, but they also have a z component. But look, they're in the exact same plane. The span of those is the exact same as the span of the original ones. So that's kind of my argument, my one example argument as to why the span of row reduced ones is the same as the span of the non-row reduced ones. Okay, there and there. The null, we found a basis for the null space. It's right here, for a -1/2 and 1. And I have this somewhere. There's the null space vector. That's not the null space vector. Something's wrong. Oh, I know it's wrong. Dang it. The scale's off. I'm trying to make it so that there. So now 1 up is about the same distance as 1 over. Okay. So, all right. There. Now we can analyze this a little better. What do you notice about the null space basis? Seth? It looks normal to the plane. It's perpendicular to the plane. And it is. It always is. So why is the null space always orthogonal to the row space? Well, if you think about the system AX equals 0, and we think about A as a couple of, if we think of it as a couple of row vectors, then to get this 0 vector here, well, how do we get that 0 vector? And this 0 vector in our case is two-dimensional. Well, A1 dot x bar is going to get us the first entry, and A2 dot x bar is going to give us the second entry. Now, this is a shorthand for what happens when we actually do the multiplication. I just think of it as dot products. I can take this Oh, I didn't write it up. Yeah, here it is. I can take this XYZ, dot it with the 1, 2, and -3, and I get B1. I can take the whatever XYZ you give me, dot it with the -1, 2, 5, and I get B2. Okay, so I can think about it as dot products. Well, both of these dot products are 0. What does it mean when we about the vectors when we get dot products that are 0? They're orthogonal. And so this X is orthogonal to both of the vectors in the row space. And so it's going to be perpendicular to the span of all of those that row space. So, so it's always, the null space is always perpendicular to the row space. And this gives us a way to think about I tried to do this more in depth in the last class and didn't go so well, but I'll just try to talk about it. Any point you give me, this, I think I have a point L here, okay? Any point you give me, I can find the projection of that point into the row space and the projection onto the null space. Basically, I can get to that point by traveling in the row space and then moving in the direction of the null space. But when I move in the direction of the null space, it won't change. That movement won't change the value of a times x. Okay? Because what happens when I change? What happens when I move in the direction of the null space? I'm just adding a piece that the dot product will be 0 with. So if I think of I did a different example in the last class. It was easier to talk about this with, but we'll visit this example. We'll visit the easier example tomorrow at the beginning of class. Okay. This is better for some things. The other example is better for the other things. So the input space. The key idea here is the input space, you can think about it as being chopped up as the row space and the null space. Okay? Any point in there can be thought of as it's some part of the row space and plus some part of the null space. What about the column space? Where does that show up? Well, the column space is the outcome. And in this case, it's two-dimensional, right? So we can represent the values. We can represent the values of the outcome. Oh, what's wrong with this? I can't move it up and down. Dang it. I love technology. Not as much as I love you, but I still love technology. Okay. Yeah, anyone know what that's from? Napoleon Dynamite. Good job. So, oh, there we go. I can get a little bit. I don't know. It's not letting me go down very far. Okay, so this point, what I have this set up as is I multiply L, that point, by the vector A, and the two-dimensional output I get is that E that's moving around down there. So, but let's look at what E's doing. Look at all the E points. All those points are in the XY plane. So, yeah, they're just two-dimensional. So the column space tells me where my outputs are when I multiply any vector from my input. And the input space can be chopped up into the row space and the null space. And any direction in the null space gets mapped to 0. And so really all I care about on this input, if I move this L and I could move it perpendicular to the plane, the value I get from this L when I multiply by A would be exactly the same value as the point that's a projection of L onto that plane. Any point that goes through L that's perpendicular to that plane, oh, maybe I can generate this. So there we go. Any point on that line, if I take any point in that line, multiply by 8, I'm going to get the exact same value. Any point on that line. And that's because the component that moves out away from the plane, that moves in the direction of the null space. And adding that piece in that direction doesn't change my outcome. Because a times that direction is just 0. So any point in here, I can think about the projection of it onto the row space and then moving the direction of the null space. But really all I care about is where is the projection on the null space. That's all I have to care about if I'm really trying to find a times x. So I can simplify things when we're doing computations. Okay, questions about row space and null space and column space? Yes?
So we can represent any point two dimensions as like some point on the row space and then some amount of null space in the positive or negative direction. Is that any less data than just having two coordinates?
Well, if you have a 3x3 matrix and you row reduce it, and it turns out you're not linearly independent, and your row space is only one dimension, really you're like all you really care about is where on that one dimension you're in the row space you are, like the projection down to that one dimension. And you're only going to end up on one dimension in your column space. So your output's only going to be one dimensional. So it might be a line in R3, but so basically you can simplify it to say, I really am just starting on a line and I'm really just going to a line. That's like all the most important information in that matrix. Even though I've written down a 3x3, if it's only got rank 1, you start on the line, you end on a line. So you can simplify it. You can simplify that. So your null space might here your null space is just one vector, but it might be that your row space is one-dimensional and your null space is two-dimensional. So then you have a line and the null space is a plane that's perpendicular to that line. So any point in the same plane in the null space, any point in that is going to be the exact same value multiplied by a as just the point on the line that plane slices through. So I know this is so hard to get your head around. I spend hours getting my head around it, and then I come in and try to make it clear. But I know I don't do a great job. You guys need to be with me when I'm doing my 3 hours of prep and trying to get my whole head around it, and then because yeah, it's not the same when I do all the work and then try to just summarize it for you guys. Yes.
If I'm kind of understanding this right, you can use these bases to form some kind of like alternate coordinate system where you would use the row and null to get to somewhere on column space, right?
Yeah, so that comment for those online was we can use the row space and the null space and use an alternate coordinate system. Yes, and that could help to simplify what a times that. It could cut down a lot on the computation that we would end up doing just a times x, if we can easily represent it in where is this point projected onto the row space and where is this point projected into the null space? Because a times any part of the null space, that projection of the null space is going to be 0. So I can cut out a lot. So yeah, nice. Other comments or questions? Okay, have a great day.